Day 692 of doing a LeetCode problem every day until I get a job. Alright, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 3548 equals sum grid partition 2. The difficulty level is hard, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go and check out that link in the description so you can get you some. Now let's see what the question says. You are given an n by n matrix grid of positive integers. Your task is to determine if it is possible to make either one horizontal or one vertical cut on the grid such that each of the two resulting sections formed by the cut is non-empty, the sum of elements in both sections is equal or can be made equal by discounting at most one single cell in total from either section. If a cell is discounted, the rest of the section must remain connected. Return true if such a partition exists, otherwise return false. Note, a section is connected if every cell in it can be reached from any other cell by moving up, down, left, or right through other cells in the section. Alright, y'all, so that may seem a little bit confusing at first, so let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So, in example 1, we have our input grid equals a 2D array of integers or an n by n matrix with the first row being 1, 4 and the bottom row being 2, 3. So it's important to remember that this is the top row and then this array right here is the bottom row. Boom, the output is true. It says a horizontal cut after the first row gives sums 1 plus 4 equals 5 and 2 plus 3 equals 5, which are equal, thus the answer is true. So let's break this down one step further. We want to see if it is possible to separate this grid with either horizontal line or vertical line such that each section is equal, and it says the sum, well, it says each of the two resulting sections formed by the cut, sorry y'all, each of the two resulting sections formed by the cut is non-empty. So boom, these are not, every cell in here is non-empty, so it passes that requirement. Then it says the sum of elements in both sections is equal or can be made equal by discounting at most discounting at most one single cell in total from either section. So in this case, they're already made equal. 1 plus 4 is 5, 2 plus 3 is 5, so we don't need to discount anything, so we can ignore this. But it also says if a cell is discounted, the rest of the section must remain connected. But the explanation says the horizontal cut after the first row gives sums 4 plus 5, 1 plus 4 equals 5, and 2 plus 3 equals 5, which are equal. Thus, the answer is true, y'all. So it's similar to yesterday's question, which was equal sum grid partition 1. Nothing much changed from that. So let's take a look at example 2. So in example 2, our input grid equals a 2D array of integers or n by n matrix grid. First row being 1, 2, bottom row being 3, 4. This time the output is true. Explanation says a vertical cut after the first column gives sums 1 plus 3 equals 4 and 2 plus 4 equals 6. By discounting 2 from the right section, 6 minus 2 equals 4. Both sections have equal sums and remain connected, thus the answer is true. Boom. So this is a case where we get to use one, or we get to discount one of the cells. So in this case, we're going to use a vertical cut, boom, right here, as you can see, and we have 1 and 3 on this side and 2 and 4 on this side. If we can, it says up here, or can be made equal by discounting at most one cell. So if we discount this cell right here, they can be made equal because now 1 plus 3 is equal to 4, and then 4 is, we have a 4 on this side of the partition as well, which is equal after we discounted this 2. Boom. So that's why the output is true, because we were able to partition it so that each sides are equal. Boom. Let's take a look at example 3 where we were not able to do that. So in example 3, our input grid equals a 2D array of integers or a matrix grid, first row being 1, 2, 4, bottom row being 2, 3, 5. This time the output is false. Explanation says a horizontal cut after the first row gives 1 plus 2 plus 4 equals 7 and 2 plus 3 plus 5 equals 10. Boom. So we split it with the horizontal cut right here. Boom. We had 7, a sum of 7 at the top, and a sum of 10 at the bottom. It says by discounting 3 from the bottom section, 10 minus 3 equals 7. So boom, we could discount this 3, and now we have 7 at the bottom and 7 at the top. But it says right here at one of the requirements is if a cell is discounted, the rest of the cells must remain connected. In this case, you see the 2 and 5 are not connected after we discounted this 3. It says they both have equal sums, but they do not remain connected as it splits the bottom section into 2 parts, 2 and 5. Thus, the answer is false, y'all. So that's why the answer is false down here, because even though we were able to make the cells or make the make both partitions even to each other, we had to discount this 3, which was in the middle of the 2 and the 5, and by discounting this 3, this 2 and 5 are no longer connected, so we have to return false, because once again it does not fit this requirement right here. Boom. So now that we understand the question, y'all, let's get into the fun part, the actual solution. Solution is not that difficult at all. Now, the first thing we need to do is compute the total sum of all elements in the grid, and then we're going to use the flat map to flatten the 2D grid into a 1D. So we are going to come right here, and we're going to say let total equal grid, or we could turn this to A. Let's turn this to A. Boom. So we'll say A dot flat map, open up the brackets, and we're going to say $0, come outside of those brackets, and we're going to say dot reduce, open up the parentheses, 0, comma, plus. Boom. Then we're going to come underneath that, and now we're going to create a helper function to check if we can split the grid into 2 parts with the equal sum or valid adjustment. So we're going to say func check, open up the parentheses, underscore G colon 2D array of integers. So square bracket, int inside, and come outside of these parentheses is going to return a boolean, open up the brackets, and we're going to use a set to store elements we've seen so far. So we'll declare a variable called scene and set that equal to a set less than int. So a set of integers, don't forget the parentheses. Boom. Then we're going to we need a variable to track the running sum of the top portion of the grid. So we'll declare a variable called top, set that equal to 0. Boom. Now we need to iterate row by row. So we're going to say for I and G dot indices. We're going to open up the brackets, and we're going to add all elements of the current row into the scene set. So we'll say scene dot form union, open up the parentheses, G square bracket I. Boom. Now we're going to add current row to the sum of the top portion. So we'll come underneath this, and we'll say top plus equals G square bracket I. Come underneath that, we're going to say dot reduce, open up the parentheses, 0 comma plus. Then the difference between top and bottom portions, we're going to get that by saying we're going to come underneath this, and we're going to say let D equal top minus, open up the parentheses, total minus top. Boom. Now we're going to check several direct conditions, right? So we'll come underneath this, and we'll say if D equals 0 or 2 vertical lines, meaning it's perfectly balanced. Then we'll come underneath that, we'll say or, so those 2 vertical lines is or. Then we'll say D equals G square bracket 0 square bracket 0. and that's going to see if it matches the left corner. Come outside of that, we'll say or two vertical lines, boom. Then we'll say D equals G square bracket 0, come outside of that, dot last, put an exclamation point, or two vertical lines, see if it matches the top right corner. Then we'll come underneath that, we'll say D equals G square bracket I square bracket 0. And that's going to see if it matches the current row's first element. We'll come underneath this, open up the brackets, and we'll return true. Boom. Now if the grid has more than one column and we are past the first row, we're going to check if we have seen an element equal to D. So this is going to allow removing one element to balance the partition. So we're going to come underneath this right here, and we're going to say if G square bracket 0, come outside of that, dot count is greater than 1, and two and signs, I is greater than 0, and two more and signs, seen dot contains, open up the parentheses, passing D, then we'll open up the brackets and we'll return true. Boom. Otherwise, no valid partition is found, so we could come underneath this and we could say return false. Boom, but we're not done yet because that was the helper function. We still need to get back into the main function. So first we need to transpose the grid and convert columns into rows so we can reuse the same logic. So we're going to say let T equal an array, open up the parentheses, open up some more parentheses. We're going to say 0 dot dot less than a square bracket 0, come outside of that dot count, come outside of that parentheses, but still inside the other one, say dot map, open up some brackets. We're going to say JNA dot map, open up some more brackets, and we are going to say $0 square bracket J. Boom. Now we need to check four cases: the original grid from top bottom, reverse grid to bottom top, transpose grid left to right, or the reverse transpose right to left. So we'll come underneath this, we'll say return check, which is our helper functions, open up the parentheses A, or two vertical lines, check, open up the parentheses, A dot reverse, put the parentheses, come outside of that, two vertical lines, check, open up the parentheses, T, come outside of that, two more vertical lines, check, open up the parentheses, T dot reverse, put some parentheses. Boom, y'all. That should be all she wrote. Let's give this a run. Make sure it runs properly before we submit it. Let's see, it's accepted, so let's go ahead and submit it. Make sure it's still accepted after we submit it. Let's see, and look at that, y'all. 273 milliseconds beats 100% of users. That's what I'm talking about. That's what I'd like to see, y'all. So before we go, make sure you get one more look at the code. This is the top part, and this is the bottom part, y'all. And yeah, with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.